Welcome back to Calculus 2. This is the first of two derivative labs. We're going to begin with the function 3x plus 1 to the power 4 over 2x minus 1 squared. How do we calculate the derivative of this function? The first question you should ask is, what are the rules? What derivative rules do you apply when calculating the derivative? Clearly, this involves a quotient. So we will have to apply the quotient rule. It also involves power functions, so we will need the power rule. But we have functions inside of these power functions, and hence we will need the chain rule. So we'll need the chain rule, the power rule, and the quotient rule. And so, the derivative at the top will bring the power down, leave the inside alone, and then subtract 1 from the exponent, but then we need to multiply by the derivative of the inside. After that, we need to multiply by the bottom. Minus the top left alone times the derivative of the bottom. We'll bring the power down, leave the inside alone, subtract 1 from the exponent, and then multiply by the derivative of the inside. We'll divide all of that by the bottom squared, and so it would be to the 4th power. Now on the exam, I highly recommend that you leave it like this. After all, if you do simplify this on the exam, and if you do make an algebraic error, I will be forced to take additional points off. On the next problem, we're calculating the derivative of the square root of 5x squared minus x, which we should certainly express the square root as a rational exponent. What are the rules? We have a power rule, and we have a function inside, so a chain rule as well. We'll bring the power down, leave the inside alone, and subtract 1 from the exponent, but we're not done. We also have to multiply by, better put a parenthesis here, the derivative of the inside. Box it, ship it, it's done. On the next problem, we're calculating the derivative of cosine squared of 7x. Remember the notational convention. Cosine squared theta is, by definition, so you're just going to accept this, the cosine of theta, quantity squared. So yes, we are going to use a power rule and a chain rule, but we'll use the chain rule twice. We have to think of this as the derivative of cosine of 7x squared. So we have the square and function inside, but we have the 7x function inside of the cosine function, which is inside of the square function. So there will be two applications of the chain rule. We'll use the power rule first. 2 times the inside left alone times the derivative of the inside. I'll put a parenthesis here, and it'll be negative sine of 7x, but to that we must multiply the derivative of the additional inside, which is 7. Put a box around that and call it done. You'll be smart if you try these problems on your own, pause the video before I present the solution, and then compare your solution to mine. On the next problem, we're calculating the derivative of e to the 3x tangent of 2x. What are the rules? We have a product, two functions multiplied together, and each of those involve a composition. So we'll have the product rule and the chain rule. Remember, for the product rule, if you have f times g prime, that's the derivative of the first times the second plus the first times the derivative of the second. You should memorize the product rule in this order. That's the order you will need for derivatives of cross products in Calculus 3. The derivative of the first, that's 3e to the 3x by the chain rule, times the second left alone, plus the first times the derivative of the second. The inside has a derivative of 2. The derivative of tangent is secant squared. On problem 5, we're calculating the derivative of cosine 3x over 1 minus the cotangent of 5x, all to the power of 4. Name the rules. We have a power rule and a quotient rule and a chain rule. Multiple chain rules, at least 3 on this problem. Applying the power rule first, we'll have 4 times this quantity left alone, to the power of 1 less, 3. Now we need to multiply by the derivative of the inside, which requires the quotient rule. The derivative of the top is negative 3 sine of 3x times the bottom minus the top times the derivative of the bottom. Derivative of cotangent is negative cosecant squared. So negative negative will be positive, derivative of 1 is 0. We'll have a cosecant squared, which is going to be real hard to fit on the end of the light board, all over the bottom squared. For our next problem, we're calculating the derivative of x squared times the sine of 5x divided by the quantity 2x minus 1 to the power 5. Name the rules. We will need the quotient rule, but when we try to take the derivative of the numerator, we'll need the product rule. In addition to that, we'll also need the chain rule and the power rule. Well, product rule, quotient rule, power rule, and chain rule. We'll need everything. So when we take the derivative of the top, we'll need the product rule. Derivative of the first times the second, left alone, plus the first times the derivative of the second, that's the derivative of the top, times the bottom, left alone, minus the top, times the derivative of the bottom. Don't forget to take the derivative of the inside. All over the bottom squared. And when we take some expression to the m and raise it to the power n, that's a to the m times n. So when we square this expression, we get 2 times 5, that's 10 for the new exponent. On the next problem, and I really like this next problem, we have 12 times the quantity 3x plus cosine cubed of 7x to the power of 4/3. I think this is an excellent exam type problem. We're going to need to use a chain rule and then another chain rule, and we have a cosine inside of that cube, and inside of the cube we have a cosine inside of the cube, That's another chain rule. And a 7x inside of the cosine. That's another chain rule still. So nested chain rules here. We'll bring the power down. Do the division by 3 first. 3 goes into 12. 4 times 4 is 16. Leave the inside alone. Subtract 1 from the exponent. And now we multiply by the derivative of the inside. Derivative of the first term is 3. On the next term, we have to take care of this power first. So it's 3 cosine squared of 7x times. The parentheses here will be critical. The derivative of the cosine next is going to be negative sine of 7x, but then you have to multiply by the derivative of 7x, which gives you one more factor of 7. Make sure you get the parentheses right. Problem 8 is an implicit differentiation problem. You start with 3x squared, y to the fourth, minus 7xy plus y squared equals 6. You can see that we'll have product rules, not only a power rule on this term, also a chain rule. Remember, this represents the y function inside of the square function. So when you take the derivative of y squared, you do get 2y, but it's times y prime. Anytime you take the derivative of y with respect to x, you'll end up with a factor of dy dx. So on this first term, we'll have 6x y to the fourth plus 3x squared times the derivative of the y to the fourth. That's 4. That's 4 y cubed times a dy dx, or y prime for simplicity. On the next term, maybe for your sake, I'll write this as minus 7 times the derivative of the quantity xy, and just apply the product rule to the xy. Derivative of x is 1 times y, plus x times derivative of y with respect to x is y prime. And then plus 2y prime, and the derivative of 6 is 0 because it's constant. The terms that have a y prime are the underlined terms. The other terms are going to have to go to the other side. So we'll have y prime times this 12 x squared y cubed, and then we'll have a minus 7x plus 2y equals minus 6x y to the fourth. We have a minus 7y brought to the other side is plus 7y. So the derivative is negative 6x y to the fourth plus 7y over 12 x squared y cubed minus 7x plus 2y. On the next problem, we're calculating the derivative of 2 to the power of 3 to the power of x. We'll have the chain rule and rules for derivatives of exponential functions here. We have an inside function and this outside function. Remember, the derivative of b to the power x is natural log of b times b to the power x. So we'll get natural log of 2 times 2 to the power of 3 to the power of x, but then we have to multiply by the derivative of the inside function using the chain rule. And that's going to be natural log of 3 times 3 to the power of x. The next couple of problems are going to make you think about the rules. What is the derivative of x to the power pi? By the power rule, you know that if you have x to the power of r, the answer is r x to the power r minus 1. So here it's going to be pi x to the power of pi minus 1. The next problem is a little different. On the next problem, you're calculating the derivative of pi to the power of x. Here, if you're taking the derivative of b to the power of x, you get the natural log of b times b to the x. So the answer here is natural log of pi times pi to the x. This next problem is a very nice trick. What if we're calculating the derivative of pi to the power 5? Well, the answer is 0, of course, because pi to the power 5 is constant. How do we calculate the derivative of x to the power of 1 over x? This one's a little tricky. It's best if you first rewrite this as y equals x to the power of 1 over x, and then take the log. This is neither a power function or an exponential function because you have a variable here and variables up here. So one way of dealing with that is to take the natural log on both sides and use a property of logs to take the power down, because now you have a product on the right-hand side. On the left-hand side, we require the chain rule. When we take the derivative of natural log of y, we will get 1 over y times y prime by the chain rule. On the right-hand side, the derivative of 1 over x is negative 1 over x squared times the second plus the first times the derivative of the second. The only thing left to do is to solve for y prime. So we'll have, let's see, I'll rewrite this as 1 over x squared minus 1 over x squared times the natural log of x, but I have to multiply the y over, and y is x to the power of 1 over x. And there's your derivative by logarithmic differentiation. On our next problem, we're taking the derivative of the quotient cosine x minus cotangent squared x over cosecant x plus secant x. You can tell I'm playing on your fears with trig functions here. We'll have to use the quotient rule, power rule, chain rule. So let's get to it. For the derivative of the top, we'll start with a negative sine x. Next we'll have minus 2 cotangent of x times the derivative of cotangent, which is negative cosecant squared x. That's the derivative of the top times the bottom Now we're going to have a problem. We're going to run out of room on the board here. I'll write it like this. A big left parenthesis here for the numerator. We have all of this. What comes next is minus the top times the derivative of the bottom. The derivative of cosecant is negative cosecant x cotangent x. The derivative of secant is secant x tangent x. And then we'll close this parenthesis here. That finishes the numerator. To that, we're going to divide the denominator squared. And we'll call that done. On paper, you might be able to write this on one line, and you won't have to break this up as awkwardly as I had to do here. We're down to our last problem, where we're taking the derivative of or the hyperbolic tangent of x, divided by cosh, or the hyperbolic cosine, minus sinh, or the hyperbolic sine. I assume that most of you have no idea what I'm talking about here. So I'm going to have to make some definitions and introduce you to some concepts. I'm going to define the hyperbolic sine of x, which means, since this is a definition, you're going to accept this. It's e to the x minus e to the minus x over 2. Why? Because I said so. You'll see more about this as we discover some of the properties of the hyperbolic trig functions. The hyperbolic cosine is e to the x plus e to the minus x over 2. These two functions have some interesting properties, but along the way I'm going to define the hyperbolic tangent, in the obvious way, sinh over cosh. Something you can see right away is that the derivative of the hyperbolic sine, derivative of e to the x, is e to the x. The derivative of e to the negative x gives me another negative. So I'll have e to the x plus e to the minus x over 2. But you'll see right away that that's cosh. So the derivative of sinh is cosh. How about the derivative of cosh? Let's find out. Derivative of e to the x is e to the x. The derivative of e to the negative x is negative e to the negative x. And here we get not negative sinh, just positive sinh. So the derivative of sinh is cosh, and the derivative of cosh is sinh. What about the derivative of tang? In order to derive the formula for the derivative of tang, you need to know an identity. And the identity is this: cosh squared x minus sinh squared x is 1. These hyperbolic trig functions satisfy identities similar to the circular trig functions sine and cosine, etc., but always a little bit off. And this is pretty easy to prove. So we should prove this. Let's start with cosh squared, that's e to the x plus e to the minus x over 2 squared minus e to the x minus e to the minus x over 2 squared. If this ends up being 1, the theorem is proved. We'll have a denominator of 4, so I'm going to factor a 1/4 out. When we square this first binomial, we'll get the e to the x quantity squared, that's e to the 2x, because you multiply those exponents. There's always the first times the last times 2 when squaring a binomial. If I take e to the x times e to the negative x, I have to add the exponents. And x plus negative x is 0. E to the 0 is 1 times 2, first times last times 2. That gives me 2 next. And then the last term squared is e to the minus 2x. From that we subtract the square of the other binomial. The only thing that's going to change there is we'll get minus 2 and then plus e to the negative 2x. Now, the e to the 2x's go because we're subtracting them. The e to the minus 2x's go, but 2 minus negative 2 is positive 4 times 1/4 gives you 1, and the proof is over. You can parameterize circles with the circular functions. The identity we just proved shows that you can parameterize hyperbolas with hyperbolic trig functions. Now, what is the derivative of tang? Well, it's the derivative of sinh over cosh, which means we need to use a quotient rule. Derivative of the top is cosh times the bottom. That gives me cosh squared minus the top times the derivative of the bottom. But the derivative of cosh is sinh. So I'll end up with sinh squared all over bottom squared. Now don't be trying to cancel the cosh squares because you may not cancel from terms. But what you can do is recognize that the numerator is 1. So what is 1 over cosh squared? Should that not be the hyperbolic secant squared? So the derivative of tang is sech squared. it's possible to prove that if you have a wire with free ends suspended between two posts, the shape of the curve, if the wire sags under the influence of gravity, is in the form of the curve of a hyperbolic cosine. Now back to our problem. Calculating the derivative of tanh over cosh minus sinh. Well, the quotient rule. Derivative of the top times the bottom minus the top times the derivative of the bottom, all over the bottom squared. And now we're done.